Welcome to another module in this massive open online course. So, we are looking at the Hilbert transform for the generation of the single sideband modulated signals, and we also looked at a frequency domain description of the Hilbert transform. Alright. So, now let us look at the time domain description, that is the impulse response of the Hilbert transform. So, we are looking at the impulse response of the Hilbert transform. The impulse response of the Hilbert transform, and we have denoted this by Ht of t, and this is the impulse response of the Hilbert transform. All right, we are denoting it by Ht of t. To start with, let us recall that the frequency response of the Hilbert transform is minus j sin f, which looks something like this. Remember, for convenience, I can always denote it by this. It is j for f less than 0 minus j for f greater than 0 and f equal to 0, this is 0. So, this is your minus j sin f. And to derive the impulse response of the Hilbert transform, we already said that we are going to use the derivative property of the Fourier transform, alright, and I am going to talk about that shortly. But first, let us look at the derivative of the sine function. Let us go back to looking at sine of t. Okay, so this is your sine of t. It is 1 for t greater than 0, minus 1 for t less than 0, and at t equal to 0, it is 0. So, sine of t we already know, sine of t equals 1 for t greater than 0, 0 t equal to 0, minus t for t less than 0. And now you can see the derivative of sine of t. Now, here in this region sine of t, that is for t less than 0, sine of t is constant. So, in this region d by dt of sine of t equal to 0 for t less than 0, right. You can see it is flat. For t less than 0, sine of t is minus 1. So, d by dt the derivative is 0, because it is a constant for t less than 0. Similarly, for t greater than 0, sine of t is again a constant, it is equal to 1. So, therefore, the derivative is again 0. So, in this region also d by dt sine of t equal to 0 for t strictly greater than 0. Alright. So, for t both t strictly less than 0 and t strictly greater than 0, the derivative of sine of t is 0, because sine of t is constant in both these regions. The only place where the derivative of the sine function, that is sine of t, is non-zero is at the point t equal to 0, where it is transitioning from minus 1 to minus 1. It takes a step jump from minus 1 to 1, and there the derivative, you can see, since the magnitude is changing from minus 1 to 1, that is the magnitude is changing by 2, the derivative is 2 delta t. Alright. So, in this position at t equal to 0, at t equal to 0, there is a step change of magnitude equal to 2. Therefore, d by dt of sin t equals 2 delta t at t equal to c. Therefore, the derivative of this function. So, you can see it is constant, step change at t equal to 0 and again constant for t greater than equal to 0 for t greater than 0. Therefore, the derivative is basically twice delta t, alright, since the change occurs only at, so t equal to 0. So, therefore, d by dt of sin t equals 2 delta t, which is non-zero only for t equal to 0, okay, which implies, now let us start with the Fourier transform of the derivative. I will show why this is convenient to find the Fourier transform of the original function. Fourier transform of d by dt of Fourier transform of d by dt of sin t d by dt of sin t is 2 delta t. Therefore, the Fourier transform of d by dt sin t equals the Fourier transform of 2 delta t, but the Fourier transform of 2 delta t is simply 2, because the Fourier transform, or we can write one more step, that is twice the Fourier transform of delta t which is equal to 2. So, right, Fourier transform of delta t is simply 1 over the entire frequency domain. However, we also have a result which states that the derivative of, that is the Fourier transform of the derivative of a function, that is if, consider this is the derivative property of the Fourier transform. The derivative property of the Fourier transform states that if a signal x t has Fourier transform x f, then the derivative of x t, that is if I look at the derivative of x t, the Fourier transform of the derivative of x t is j 2 pi f times x f. The Fourier transform of the derivative of a signal x t is j 2 pi f x f, where x f is the Fourier transform of x t. And using this property, the Fourier transform of the derivative of sin t, therefore, the Fourier transform of the derivative, that is the f t of the derivative of sin t, that is j 2 pi f Fourier transform of sin t. However, we have already seen that the derivative of the Fourier transform of sin t, from here we have seen that the derivative of the Fourier transform of sin t is 2, alright, and therefore, this is also equal to, from above, this is also equal to this result we have from above, which implies that these two must be equal. So, this implies we must have j 2 pi f Fourier transform of sin t equals 2, alright. We have already shown that the derivative of the Fourier that the derivative, that is the derivative of sin t is 2 delta t, therefore, the Fourier transform of the derivative of sin t is 2, and we also from the derivative property of the Fourier transform we are seeing that the derivative of sin t has a Fourier transform, that is j 2 pi f times the Fourier transform of sin t. Therefore, these two quantities must be equal, which implies j 2 pi f Fourier transform of sin t equals 2, which implies that Fourier transform of sin t equals 2 by j 2 pi f, which is basically equal to 1 by j pi f. Therefore, sin t, Fourier transform sin t has the Fourier transform 1 by j 1 over j pi f. This is the property that we have been able to derive. Sin t has the Fourier transform 1 over j pi f. All right. And now let us use duality. Let us now use duality and using duality. Remember, duality says that if x t has duality property of Fourier transform, which states that if x t has Fourier transform x f, then x t has Fourier transform x of minus f. Using the duality property, we have sin t has Fourier transform 1 by j phi. So, using the duality property, if sin t has Fourier transform 1 by j pi f, 1 by j pi t has Fourier transform x of minus f, that is sin of minus f. Now, remember, sine function is an odd function, right, because it is 1 for t greater, sin t is 1 for t greater than 0, minus 1 for t less than 0, 0 at equal to 0. This is an odd function. So, sine of minus f is minus j sin f. This is sine in the frequency domain, by the way. So, this is minus, which is exactly what we want for the Hilbert transform. This is minus j sin f. This implies that 1 by j pi t has Fourier transform minus sin f, sorry, not minus sin of minus f, is minus sin f. So, 1 by j pi t has Fourier transform minus sin f, which implies, now taking the j to the other side, 1 by pi t has the Fourier transform minus j sin f. 1 by pi t has the Fourier transform minus j sin f. Now, minus j sin f is nothing but, recall that minus j sin f is nothing but the impulse response of the Hilbert transform h t of f, which implies that 1 by pi t, which is the inverse Fourier transform of this, must be nothing but the impulse response of the Hilbert transform. Therefore, the impulse response of the Hilbert transformer is 1 by pi t, and that is what we have derived. H of h t of t equals 1 by pi 1 by equals 1 by pi t. Okay. So, that is a property that we have been able to show, that the impulse response of the, that is a, remember, the Hilbert transform is a linear time invariant system whose Fourier transform is given by minus j sin f. In the time domain, its impulse response is 1 by pi t. Therefore, now if you look at the Hilbert transform, remember the Hilbert transform is an LTI system, correct. This is your Hilbert transform is an LTI system. If you pass the signal mt out comes the Hilbert transform m hat of t, this is your signal. This is its Hilbert transform of m t of m t, and now this system has Fourier transform we already see in this equals minus j sin f. In fact, this is a phase shifter, correct. Remember, this is a phase shifter, that is, it shifts the phase of all the positive frequency components by minus pi by 2, all the negative frequency components by pi by 2. This is a phase shifter. It has frequency spectrum, the Fourier transform is minus j sin f and the frequency, and now the impulse response, we have derived the impulse response h t of t equals 1 by pi t, which implies in the time domain the Hilbert transform can be represented equivalently as m hat of t equals the input signal. Remember, when you pass input signal through LTI system, signal gets convolved with the impulse response. So, m t convolved with 1 by pi t. This is the time domain representation of the Hilbert transform. This is the time domain representation of the Hilbert transform, and this is, remember, convolution. This is a time domain representation, therefore, it is a convolution in time domain. That is convolution of the input signal with the impulse response. Now, frequency domain representation, that is the output Fourier transform. Remember, convolution in time domain is multiplication in the frequency domain. So, this is mf into h t of f, which is basically your mf times minus j, the product, correct. This is a product, or you can write this as minus j sin f times okay. So, this is the product in the frequency domain. So, this is the frequency domain representation of H t Hilbert transform. And this is a multiplication in the frequency domain. This is a multiplication in the frequency domain. All right. So, in this module we have developed the time domain representation of the impulse of the Hilbert transform. That is, we have calculated the impulse response of the Hilbert transformer using two properties. One is the derivative property of the Fourier transform and the duality property of the Fourier transform, to demonstrate that the impulse response of the Hilbert transform is 1 over pi t, which corresponds to the spectrum of the Fourier transform of the Hilbert transform, which is given by, or the spectrum of the Hilbert transformer, which is given by minus j sin f. alright, and therefore the Hilbert transform can be represented in the time domain also equivalently by the convolution, that is m hat of t, which is the Hilbert transform of mt, is given by the convolution of mt with 1 over pi t. However, as you can see, since 1 over pi t is a messy signal, correct, 1 over pi t is quite a messy signal, therefore it is much more easily readily expressed in the, it is much more, this signal is much more readily expressed in the Hilbert transform. The operation of the Hilbert transform is much more readily expressed in the frequency domain rather than the time domain. So, the frequency domain specification of the Hilbert transform, which is the phase shifting property, that is minus j sin f, alright, where it's which shifts the phase of all the positive frequency components by minus pi by 2 and the negative frequency components by pi by 2, is much more simpler compared to the time domain description of the Hilbert transform. Alright, so we will stop this module here and continue with other aspects in the subsequent modules. Thank you.